Each charge on its own can create an electric field. Each charge on its own also has an associated electric potential. This is our equation for the electric potential due to a point charge. And that's equal to the Coulomb constant times the charge divided by the distance from the charge and where you're evaluating the electric potential. This looks a little bit different from our equations for the electric force, our equations for the electric field. Instead of being inversely proportional to the distance squared, it's only inversely proportional to the distance. Now this is our charge. We've got a positive charge. We've got the electric field lines that are leaving outward and away, pointing outward and away from our positive charge. All of these green rings around it are what we call the equipotential surfaces. That's in the next slide. Now here is a graph that shows it compares our electric field to our electric potential. Here's the distance r that you are away from a charge. Then we see that this blue line here is the curve for the electric potential as you move away from the charge. The orange line here is the curve for the electric field as you move away from the charge. So they're both equal to Coulomb constant times Q, but the electric potential is divided by R, whereas the electric field is divided by R squared. And so you can see that because of that difference between inversely proportional to the distance or inversely proportional to the distance squared, that the electric field diminishes quicker as you move away from the charge than the electric potential as you move away from the charge. The total electric potential at some point P due to multiple charges is just the sum of the electric potential due to the individual charges. Just like it was for the electric field and electric force, it's the sum from all the charges acting together at that one point. But it's way easier for our electric potential because it's not a vector. Now this electric potential diminishes as we move away from a charge. We can identify what we call equipotential surfaces. Equipotential. Equa means equal. Equal potential surfaces. These are all points that have the same electric potential away from a charge. It's easy to draw the equipotential surfaces around a single charge. Here's our single point charge again, positive charge. We've got our electric fields here in blue emanating away radially. All these green lines here, those are points all around that charge that have the same electric potential. And so we would call this an equipotential surface because any point around this green ring, let's say this outer green ring, any point along this outer green ring, let's say, you would have the same potential. The electric field at every point on an equipotential surface is perpendicular to that surface. So let's take this equipotential surface here, and we see that the electric field is perpendicular to it everywhere around that equipotential surface. Work is required to move a charge at constant speed between equipotential lines. That makes sense because each equipotential line identifies a region around a charge where the equipotential is the same. So between two equipotential lines, you're going to have a difference in potential. So because of that, you have some work required to move your charge between those. But no work is required to move a charge along an equipotential line. If you're on one of these equipotential surfaces, if the potential is the same, there's no change in the potential, there's no potential difference. So you don't have to do any work to move your charge around this ring, but you do have to apply work in order to move the charge from, say, this outer ring here to the next ring in, or any of the others. We can also draw equipotential surfaces between our parallel plates. We've got our positive plate, our negative plate. We've got the electric field lines between, pointing from positive to negative. And then we have our equipotential surfaces. Those are these vertical lines here that identify points away from the plates where you have the same potential. So as we go from 100-volt potential at our positive plate to 0-volt potential at our negative plate, you can identify these nice demarcations in here where the potential decreases from 100 all the way down to 0 volts. Here are some more equipotential surfaces, some that are a little bit more interesting. Here we have two opposite charges. We've got the electric field coming from the positive charge toward the negative charge, and we've got our equipotential surfaces. So right down the middle, we have an equipotential surface right between the two. Actually, at that point right there, we've got the electric field is going to be pointing off toward the exactly perpendicular to this equipotential surface here and pointing off to the left. And then we've got these other rings around the charges to represent the equipotential surfaces. The potential is greatest or most positive near the positive charge, and it's the least or most negative near our negative charge. And you see that the potential is not necessarily the same value at the same distance away from the charge. You can really see evidence of this last statement within this figure right here, which shows that equipotential surfaces around two charges with the same sign. In this case, we have negative charges. And you can see how those surfaces are not the same in all directions around either of the charges. And actually down here, we could look even closer. This first equipotential surface around each of the charges is drawn at -10 volts. This next equipotential surface is drawn at -5 volts, and this outer one is drawn at -2 volts. So it's all just a consequence of summing up those electric potentials from those charges at different points away from the collection of charges. This is a really great PHET simulation where we can look at the electric field and electric potential between point charges. Here I have a positive charge of 1 nanocoulomb, a negative charge of 1 nanocoulomb, and I can put up the electric field lines. We see that the electric field is leaving from the positive charge, it's going toward the negative charge. I can also, well, what I've clicked here shows us a little bit about the magnitude of the potential or the voltage around these charges. It's strongest where it's brightest red or brightest blue. I can also bring in this meter here, and it will tell me the potential at any point within this screen here due to the presence of both of these charges. So the potential at any one point is the sum of the potential at this point from this charge and the potential from the other charge. And you could use this meter to map out equipotential surfaces, actually. That's why it's labeled equipotential. Just hover it around and you find every point where you have the same value for the potential, and you could connect those dots and it would give you an equipotential surface. Actually, it might be a little bit easier to do this with two negative charges. Let's bring in two negative charges here. And with these two negative charges, we're going to see about the same value of equipotential, if I do this right, in a concentric ring around each of these charges, very close to, okay, around each of these charges. And then when I get a little bit further out, it was kind of like that, like, I don't know, wrench shape where we could get similar values of equipotential from that previous image that we saw. And then you could go all the way out and do this sort of elongated cigar shape in order to get other values for another equipotential surface. In any case, you could map out equipotential surfaces in this way by using this little meter to find every point where the potential at that point is the same value. You connect all of those lines and then you get your equipotential surface. It's kind of like a contour map in geography.
In a previous mini lecture, we found the electric field at a point P due to two charges. And actually, I left that diagram up right here. And it took us a lot of time and a lot of work to get that electric field. We're going to see that the electric potential, finding the electric potential, is a lot easier. So our electric field is the force per unit charge that is experienced by a test charge that might be placed at that location. The electric potential is a little bit different, and it's the work per unit charge required to move a test charge from infinity to some point away from these two charges here. So imagine we had some little test charge and we're trying to bring it in from way at the edge of our solar system to this point P right here. And so the work required for us to bring that charge in is the electric potential. Now, in this problem, we had a 7 microcoulomb charge at the origin and a -5 microcoulomb charge located at a distance 0.3 meters away along the x-axis. And then we are going to find the electric potential, or previously we found the electric field, of a point right here, and this point is 0.4 meters above my charge that's sitting right here at the origin. I've placed this charge at the origin. So a 7 microcoulomb charge is at the origin, and a point charge of -5 microcoulombs is on the x-axis at 0.3 meters away. Find the total electric potential due to these charges at a point with coordinates 0, 0.4 meters. So it has a y component of 0.4 meters and no x component. Okay, and we already drew in this triangle here that gives me this distance 0.4 between my charge and the point P. I've got this distance here between my two charges, which was 0.3 meters. Now to get this distance here between charge 2 and the point where we're evaluating the electric potential, well, we've got a right-angled triangle right here. Okay, so we've got a leg of 0.4 meters, another leg of 0.3 meters, so we've got c squared is equal to a squared plus b squared. Or we could call this distance r. R squared is equal to x squared plus y squared. And we found that this length here, the hypotenuse of this little triangle I could draw with my charges and my point P, the hypotenuse of that triangle was 0.5 meters. Okay? So now with that information, we can evaluate for the electric potential at point P right here. Now the electric potential is way easier to find than the electric field. To find the electric field, we had to find the x and y components of the electric field due to charge 1 and the electric field due to charge 2. And then we had to add the x and the y components of E1 and E2 together in order to get the x and y components of the electric field at point P, the total electric field at point P. And we found that that total electric field at point P was 2.71 times 10 to the 5 Newton per Coulomb at 66.6 degrees from the positive x-axis. We had to do all of that work. There was a lot of work in this problem because the electric field is a vector, but the electric potential is a scalar. So we care about the magnitude, but we don't care about the direction, and that makes our lives a whole lot easier. So then to find the electric potential at point P, it's just going to be the electric potential from charge 1 at point P plus the electric potential from charge 2 at point P. The potential is a scalar, not a vector, so we don't have to worry about getting all those vector components, right? We just straightforward use the equation for the electric potential. Then let's just jump in and find our electric potential at point P due to charge 1. And that electric potential, equation for electric potential is our Coulomb constant times Q1 all over R, I'm going to call it R sub 1. It's this distance between Q1 and my point P. So this is going to equal 8.99 times 10 to the 9 Newton meters squared over Coulomb squared times Q1 was 7 times 10 to the minus 6 coulombs, that's a microcoulomb, divided by the distance between them, which is 4 meters, or 0.4 meters, 0.4 meters. Then this electric potential is 1.57 times 10 to the 5 volts. Our unit on electric potential is the unit of a volt. 1 volt is 1 joule per coulomb. Then to find the electric potential at point P due to charge 2, that's going to be K times Q2 over R2. So that's 8.99 times 10 to the 9 Newton meters squared over Coulomb squared times charge 2. We are going to put in the minus sign here, minus 5 times 10 to the minus 6 coulombs, all divided by this distance between charge 2 and point P, which is 0.5 meters, the hypotenuse of that little triangle there. Then this electric potential is minus 8.99 times 10 to the 4 volts. Now we just straightforwardly add them together. V1 plus V2 will give us an electric potential of, there it is, 6.71 times 10 to the 4 volts. So I had to take 1.57 times 10 to the 5 volts plus minus 8.99 times 10 to the 4 volts. And that gives me this quantity here for the electric potential at point P. Now, how did we get this unit of volt from all of the stuff in here? Well, let me show you. So we have the unit for our Coulomb constant is a Newton meter squared over Coulomb squared. And then we're multiplying it by a charge, which has a unit of a Coulomb. And then we're dividing it by a distance, which has a unit of meter. Okay, so we've got this C cancels with one of these C's. I'm going to rewrite this as Newton meters squared over Coulomb. That's what my marker's running out here. Times 1 over meter, an inverse meter. We're dividing all of this stuff by m. It's the same thing as dividing all this stuff by m over 1. And when we divide by a number, it's the same thing as multiplying by the reciprocal, so I can rewrite it like this. This meter cancels with one of these, and then I'm left with Newton meter over Coulomb. Okay, well, let's see. 1 Newton is a kilogram meter per second squared. And we're multiplying it by a meter. And then we're dividing it by Coulomb. Well, finally, we've got a kilogram meters squared over seconds squared on the top. Over seconds squared on the top. And we're dividing it by this unit, Coulomb. Now this kilogram meter squared over second squared, that's the same thing as a joule. We've got a joule per Coulomb, which is also the same thing as 1 volt. So that's how you can show to yourself that yes, in fact, with this equation and using these units, we do go from all of this stuff here to an actual unit of volts. And the unit of electric potential has a unit of volt.